It sounds like someone switched on the microphone and ready to share, or not yet. Okay. Does anyone want more time for reading, or we can start discussing. So please show some signs if more time is needed. Okay, thank you. Kevin, do you have comments on work of David?
Yeah. Okay. So I read doing David's work, and I honestly couldn't think of anything to say.
Other comments? I didn't get if Kevin had a comments to David. Kevin, if you have comments, you may show them on the screen, to share the screen. If no, just answer. Do not answer. Fatima.
Yes.
Do you have some comments on David's draft?
I did not look there yet.
Okay. Okay.
I'm done with Kevin's one and I'm reading now again.
Okay. Okay. That's okay. That's okay. Thank you. As who wants to volunteer on David's? Okay. I'll probably give some comments, and then we'll go to the next. I did click on the share screen. It just shows a little delay. Okay. Well, this one is quite short, and therefore it is very pleasant and easy to read and discuss at a short time. So the first next time, maybe it will be reasonable to include figures in the next drafts, so it will be easier to follow. It looks like second figure shows must show orbitals, but the sentence is not complete. Maybe space origin in the hybrid model doesn't show substantial charge.
It looks like I didn't finish my thought.
Huh?
Looks like I didn't finish my thought.
Oh, okay. So probably it doesn't show substantial charge density, right?
Yeah.
Okay. Then in the figure 3, it also ends with that one can see increase in the gap, and one can add that it is due to quantum confinement, so that offer an answer to a curious reader. And maybe it would be reasonable to have a plan of the remaining figures, because all the orbitals and density of states will not be competitive. And we all know that you have much more results. So even if they are incomplete, it's a good time to line them up and design a logical like sequence how they will be presented. So even if something doesn't work, start planning your research, report of the research in the manuscript. Other more comments to David's work? Anything? Okay, let's go to maybe results by Aaron. Volunteers. Would you like to give some comments on Aaron's work?
Yes, I only have the question for the very last figure, because it's not as usual as our previous figures.
Okay.
So I guess my question is, what is the initial conditions?
Are you going to show?
We cannot see the localization of our initial conditions.
Would you be willing to share screen, or if you have something written, or if you don't, I can just bring it up to the shared screen.
Okay. For some reason, I cannot do it.
Okay, I'll probably then bring it up. But the sharing screen is delayed when there are many users, so it takes like 30 seconds. And it asks which, if you have more than one screen on activated, it asks which screen to share. So at the bottom there is a symbol of microphone, camera, telephone, and rectangular box for the display, and then the last one will be PDF. So if clicking on display should help.
I guess this has something to do with my browser, because it said my Firefox is blocking.
Okay, then I'll show it, and maybe next time the tech support were recommending to use Chrome for this communications. So I am bringing the work of Aaron and going to the last figure request of Evan. Let me click so that it will be the same. Okay, I'm ready.
Yes. So I guess why this is different from our conventional figures, and where is the localization of our initial conditions?
Okay.
It's the same. I don't know why the yellow blue don't come in earlier, but it's just something in the software. I would just have to figure out why it's not doing that. But it's same as everything we've done before.
So it's
And the initial condition.
so it is not your intention. This change in yellow stripes is not color code of intentional color code and of new effect.
Right.
Okay.
Okay.
And then the initial condition, if you look at the blue bars on the side, those are the electronic states. So can you see my mouse or no?
No.
Oh, but if you just follow the dotted line over to the blue line.
Aaron, I will try to serve as your mouse, but next time probably we need a speaker to share the screen and point stuff. I know we all are getting skills how to operate in this remote stuff. Are you talking about the highest of the like excitation number 4?
Yes.
Okay. And for the whole, it will be also excitation number 4?
Mm-hmm. Yep.
Okay. So it's like I, E equals 4?
Yes.
Okay. Yuan, please continue the questions or comments.
Okay, I guess another question is about the first stage. In the text, you had talked about some net charge density, and then you basically said there is some difference for the excited state and the ground state. But this sentence is quite confusing. So I guess, what do you mean? What's the meaning of that?
Can I bring it up? Which part in the text is that?
The first page, the second sentence.
Okay, I'll bring it up in like 20 seconds. This one?
Yes.
So I guess the easiest way to explain it would be to look at my figure 1. I don't know if it's possible to bring that back up.
Yes. We need to practice a little patience because everything is being delayed. But it is very possible. Done.
So the B panel, I guess that's a visual of what I was trying to explain. And so since you have different charge density inside the box, there'll be different forces acting on the nuclei. So you can get changes in the structure.
Okay.
And changes in the structure subsequently induce more changes in the electron density. Would it be correct to say so?
Yeah, and then ideally it would reach some minimum.
Okay, so this self...
the loop should stop eventually.
Okay, so it self-consistent procedure will reach convergence.
Right.
Okay. Final question is, in the text you are talking about there is some narrowing of the bromine-bromine coordination. I guess my question is, what do you mean by narrowing the coordination? Are you talking about the coordination number or just the bond length?
The length. Number would be the same.
Okay.
But I guess there's, in the B peak, in my radial distribution plots, it's like the solid line is more broad than the dashed lines. So that's what I mean by narrowing.
Okay.
Okay. Are there more comments from Yulun?
No.
Okay. Let me quickly check. Anyone else wants to give comment on Aaron's work?
I have one comment.
Oh, please.
I can see in result sections there is a sequential description of each figure, but it's not clear that what's the implication of the output of this research.
Aaron, did you get the question?
Could you say that again?
So what's the application of this output of your research? Like where it will be applicable?
Well, I guess the novelty is it's more well, I guess the story isn't like complete yet, but the idea I have in mind is that usually for quantum dots, you want all the surface to be passivated by ligands. But for the modeling that we're doing, it seems that there is ligand desorption, which creates trap states. And so essentially the end product would have a story of something along the lines of broadening of photoluminescence due to trap states.
Okay, so it's this research is applicable in photovoltaics then.
I would say no.
Since it's photoluminescence.
Photoluminescence is not photovoltaics. It's like light emitting diodes or lasers.
Okay, so it is applicable in light emitting diode.
I would, my opinion is that it is applicable. Aaron may think differently.
I mean, you could put it in a LED, but I guess what I'm modeling isn't necessarily related to LEDs.
Okay.
Okay, and maybe what Aaron is doing can be a path to assess the mechanisms and rates of photo degradation of light emitters. Some materials lose their ability to emit light if they emitting light too frequent. So semiconductors materials may experience photochemistry and experience chemical transformation that disable their ability to emit light. Or, as Aaron shows, this photochemistry may not can be not so much disfavorable. But upon photoexcitation, the structure on the surface of these materials is evidently changing, but there are no too many methods to clarify what is going on the surface. Okay, more comments to Aaron's work? Let me quickly go over. In the fluctuations of Kohn-Sham orbital energy and in the fluctuations of the lead to oxygen distances, it is because it is a short trajectory, it is not clear if the distance will continuously increase or it will perform oscillations. I'm not demanding answer right now. It's just bringing up the question. Figure 6b shows very interesting observation by two orders of magnitude that electronic states or negative polarons experience two orders of magnitude slower transitions. And one may want to add a comment that the rate of non-radiative transitions depends on spatial overlap of initial and final state. If there is a trap state, it doesn't overlap with states which are neighboring in energy, and it gives a substantial slowdown. I bet that these thoughts were sounding like self-evident for Aaron when writing, but a reader may want speculations like this. The figure 7 panel B. So Yulun attracted attention to figure 7 panel A, and I would like to attract attention to 7 part B, where the time-dependent intensity of luminescence experience instantaneous instantaneous jumps. Is it a numerical error or it is a physical effect? So also, Aaron, if you want, you may answer, but it could be just a comment for the future. Okay. Aaron, would you Who has wishes to give comments on Fatima's work? Aaron, do you have any comments?
Yeah, I have a couple.
Okay.
Or questions, I guess. So, I guess could you just pull up the figures?
Yeah, I can do it. Please pardon a little delay. It will take maybe 20 seconds. Which figure should I bring up?
3.
Okay.
So for each of those plots, could those be interpreted as like 2D slices of your figure 2? Not of the figure 2, but are you just kind of playing through that dispersion curve? Would that be how to visualize or how to interpret these figures?
Is this question for me?
I think so.
So what was the question? Yeah. Okay.
So could these figures be interpreted like if you took your figure 2 and you just cut slices through them? Would that be the same way as interpreting these figures?
It's just two-dimensional figure. How electrons are distributed in the around the direct points in Brillouin zone of graphene. There are three-dimensional figures also available, but it is preferable to put two-dimensional ones. Is this answer okay, or you answer something different? You have a question about something different.
Let me contribute to discussion. Aaron, I would say answer to your question is absolutely no. It's very interesting analogy, but it is not what Fatima is showing and discussing. The color codes in figure 3 is show eigenstates, like wave function absolute value square in the potential shown in figure 2. Last 10 seconds I was, so to say, lying with pedagogical purpose. One cannot use the word potential. This is dispersion curve. But the mathematically problem is very similar to finding an eigenstate of the wave function in two-dimensional potential. The only difference that potential depends on position and wave functions are typically depending on position. Here, the dispersion curve depends on momentum and wave functions also depend on momentum. The analogy that Aaron is bringing up is that maxima of the eigenstates are approximately localized near the minima of the potential or near the minima of the dispersion curve. So the question that Aaron is asking is logical, but the answer is no. Aaron, please continue asking questions or giving comments.
Can you go to figure 4?
Yes. Done?
Yeah, so could the fringes that are observed, could you interpret those similar to you have a wave packet bouncing off a barrier, where you have some that transmits, but then some that reflect, and then it's essentially interfering with itself?
Can you please repeat? I'm sorry.
So you have a wave packet localized at time 0, and then at later time, like it moves in the, I guess, potential of the graphene. And at later times, you observe fringes. So could those fringes be interpreted as, like in a chemical problem, if you have a wave packet that runs into a barrier, it can go through the barrier or reflect off. And then when it reflects, it can create interference patterns.
I'm not sure if there is any barrier here. I don't think there is any potential barrier.
Yes, there is a barrier because the dispersion has minima in Dirac points and maxima in between. So while wave packet attempts to go from one Dirac point to another one, it experiencing a barrier.
Okay.
So analogy that Aaron is trying to set up is very reasonable and intuitive. There is a correction. In case one would set magnetic field equal to 0, the wave packet will not move anywhere. It will keep its original distribution. Unlike potential as function of position, in momentum space, the reason to change momentum is magnetic field. Aaron, if you like, please continue to share your comments or corrections.
I guess my last comment is for figure 5.
Okay. Done?
Yeah, so yes, I don't remember my electrodynamics very well, but would the curl of that curve, that correspond to anything physical or anything useful for trying to analyze the dynamics?
Yes, it shows the center of the probability density distribution, or like how the center of the probability density distribution is moving.
Mm-hmm.
Like it's not moving very long distance, it's just short distance, as you can see from 20.079 and 20.08. It's very small distance. So it's just to show the purpose of these figures is just to show the trajectory of the probability distribution, electron distribution, trajectory of the center of the electron distribution. That's what I understand.
Mm-hmm. I guess by curl, like not necessarily that the curve is curling, but like the vector operator definition.
What was that?
So like the curl of like a vector. I guess that's what I was asking about.
Okay.
Instead of like that the curve, that it's like not that it's curling itself, but whether like if you could compute a curl, whether that would have any sort of physical meaning.
Oh, like rotor, differential operator of rotor?
Right.
Which will be analogous to expectation value of angular momentum.
Yeah.
And it will be correlated to the value of magnetic field.
Well, that's the weird part though, because it seems like in your panel B, like it stops at circular change in momentum. So it seems like it's the change of the curl, or it's like its change of angular momentum either slows down or it stops changing.
Fatima, do you have hypothetical answer?
I'm not sure.
Let me try. So this is non-equilibrium, non-stationary dynamics. The initial state is not an eigenstate of this full Hamiltonian with magnetic field. Therefore, observable expectation values corresponding to this along this trajectory are not expected to be conserved. So it is formal abstract answer, and the more mechanical answer is that wave packet can be a superposition of circular waves moving in the opposite direction, and as time passes by, some of them are getting suppressed, some of them are getting enhanced, and the overall value of magnetic momentum and overall value of the curl for this central point is going to change. So a lot of observables for Gaussian wave packets change in time. For example, in free space, in regular one-dimensional packet, the width of wave packet expands, so that some observables change in time in a non-regular, non-oscillatory fashion is not a big surprise. If this would be a purely classical electrodynamics, if the wave packet will not have a width, if it will be only one delta function which doesn't have a right to expand, then it will likely start going over circular orbit. Its expectation value will perform circular trajectory, and it will correspond to a constant value of magnetization. But it is not, and originally before calculations were started, it was one was expecting this result, but it is not what comes out of this simulation, which can be a big discovery, or it can be indication that some aspects are missing in the model. Aaron, please continue to discuss or offer more corrections.
That was the last of my comments.
Okay. Anyone else has comments to the work by Fatima? Let me very quickly go over a couple of last paragraphs in the text. It's not snapshots. When there is no dynamics, there are no snapshots. Eigenstates were chosen randomly. No, even if they were chosen randomly, reviewers will not like it. It's just some editorial corrections, spatial distribution. Eigenstates are localized or delocalized around Dirac points. I understand what is written, but maybe a slightly different verbalization could work. Maybe delocalized away from Dirac points, or it's just something doesn't sound as clear as possible. Wave nature of light. No, it is not wave nature of light. It is wave nature of electron in 2D graphene. And it correlates with the last question of Aaron. So we do not see perfect circular orbitals because there are these fringes happen because waves are hitting the walls in different directions, coming back, and something complicated is going on. So, and once again, wave nature of electron in this two-dimensional material. And here is my version of Aaron's question, like how much these trajectories coincide or differ from cyclotron trajectories. So they differ, and we may try to find speculation why. Anyone wants to add more comments to Fatima's work? Okay. Then Aaron was already presenting. David, who has questions? Who has some comments to Yulun's work?
I have a question.
Excellent. please lead the discussion and give me assignments which figure to bring up if needed.
So on figure 4.
Okay, we are on figure 4.
Yeah. Specifically part B, figure B. I'm assuming looking at this is a graphical representation of the table you had last week. Do the colors in part B correspond to the colors in part A?
Yes. They're consistent.
Okay. The other...
I didn't hear you.
I'm not sure if David is speaking right now. Oh, no, he's... David, we do not hear you. Please unmute your microphone. David, we did miss your last comments. Do we hear each other at all generally, or overall connection is lost? Okay, it sounds like Aaron at least is... Okay, I can hear everyone else. David, then you need to type your questions. Yes, if you have the connection for calling, it will be fine. Or you can call my Skype, and then everyone should hear you.
Hello?
Okay, yes, we hear you. Okay, please continue.
I have no idea where I got cut off.
Maybe your neighbors are watching movie or playing computer game.
What was my question?
So it was quite...
Your last comment, clarifying the color code.
Yeah, sure. Go.
Any other?
I guess I got a question.
Please.
So for your figure 4B, so you attribute the applied electric field for all the models with electric fields showing quicker charge transfer?
Yes, right now the conclusion from figure B is either negative or positive electric field will facilitate the charge transfer rates.
So I guess if I was a reviewer, I would ask, I guess my expectation would be is that the ordering for the charge transfer rate should be either like negative field, zero field, positive field, or vice versa.
Mm-hmm.
For the ordering. So yeah, that's the only. So if I was reviewing it, that would be my question, but I don't really have anything else to say outside of that.
Okay. Because I guess right now, at this point, we are still fitting with single exponential, but I guess maybe it's not very accurate. Mm-hmm. That's why we do not have a clear trend in this case.
Okay. Anyone else have questions to Yvonne's work? I do have a couple, and since we are focusing on this figure 4b, the rate of formation dipole is one characteristic, but there is a chance that depending on external electric field, the dipole at time equals infinity changes. And it is not reflected in the in this figure. So maybe one still needs a table with or just one line of text showing what will be the dipole. Let me bring it. Let me illustrate it with the figures. It goes extremely slow. I'll address it verbally. So in case the in figure 3, in the last panel of the figure 3, the solid and dash lines diverge. One goes to the die, another goes to titanium dioxide. But if one sets up a very large field and HOMO and LUMO swap their order, this may reverse direction of charge transfer or make it completely zero, so that even at time equals zero, time equal infinity, the electron and hole will be localized at the same place. I'm not telling that it will happen, but I would try it and report the value of a dipole at time equal infinity for each value of the field. Because the charge transfer is characterized at least by two aspects: how fast and how far. So it can be very, like, charge transfer can be very fast, but it transfers only 1% of elementary charge, or it transfers the whole electron but on a very short distance, and the reviewer may ask about it. Does it sound reasonable?
Okay.
Okay. Let's go to work of Kevin. Who has comments? Yvonne, would you like to share Anything on Kevin's work? Or just attract attention to parts that need improvement?
Okay, so I guess, can you go to page 1?
Yes.
So the last sentence of the first paragraph.
Okay,
I'm just very confused here. Here you talk about quantization of energy, but basically this first paragraph just compare doped with undoped models, right? So what's the reason you bring up the quantization of energy here?
Hello? All right, so you have a question about the last sentence of the first paragraph?
Yes.
I mean, I don't know, it seems like the right thing to do. So in this paragraph, I'm talking about the density of states. The density of states is when I think of that, I think of the equation associated with that, which is just a Dirac the delta function. All right, and from there, since these delta functions are discrete, and density of state graphs is just a bunch of them put together. That immediately reminded me of the quantization of energy, which is that energy in quantum mechanics is discrete. So that's the reason I came up with that sentence in the last paragraph.
Kevin, are you mentioning the fact that just all orbitals have discrete energies?
Yes.
Okay. Okay. So it is highlighting of the known evident fact. Okay. Yulun, should I bring up any other part of the text?
And also the last sentence for the second paragraph. I just didn't get it. What's the meaning of this sentence?
Kevin, would you like to answer Yulun's question?
Give me a quick second. Right. So in this paragraph, I'm talking about absorption spectra, and I state that that the absorbed photons show up as a dark transition because the atomic spectra shows up, and the reason I say it's a dark transition is because the photons associated with the energy that the electron absorbs aren't emitted. All of it is entirely absorbed, and none of it is emitted as visible light. So that's why I say they show up as a dark transition. You know what? Maybe this would make sense. Professor, can you pull up the current figures and show these two documents side by
side? Side by side, not possible. I will move to the figure.
Can I try from mine?
Do you mean this figure?
Yeah, that figure. So yeah, I don't know. Is it possible to show this figure and my results side by side?
No.
Oh. All right. So yeah, if you look at my Joe nanowire figure 4B, that looks like a dark condition. So I commented about that in my results section. I admit, I still have trouble understanding what a Joseph's spectra is. So I looked up Google, I looked up a Joseph's spectra, and I tried to understand it the best way possible. So that's why last sentence is in my second paragraph. So if you think I'm like misunderstanding something, please correct me.
Can I contribute to the discussion?
Sure.
So in the sentence that Yulun was asking, the correct part is that lowest transition in the doped nanowire is dark. The remaining interpretation is not canonical and probably should be removed or shortened. And the only fact that Kevin wants to highlight, if one looks at the intensity of absorption at the band gap, in the undoped, it is about 0.5 arbitrary units, and in the doped, it is 10 times smaller, 0.05. So the intensity of absorption is reduced, and on the colloquial language, the reduction of the intensity of absorption is often referred with the word dark.
Okay.
Yulun, does it answer your question? At least in part. Yulun, do you have more questions on Kevin's work or some suggestions which parts should be improved?
Can I go to page 2?
Yes.
So I guess the last sentence of the top paragraph. So basically you are saying there is some contradiction, but that's not the case, right? Because in figure 3, the band gap is obtained from geometry optimized model, but here the band gap is from one of the configuration along the molecular dynamics trajectories, right?
Professor, can you bring up the section he's talking about?
So you want?
So he said,
you want me to display the figure?
Hold on. Can you highlight the sentence he's talking about?
Yes.
All right. Sorry, Ewan. Can you say your objection again?
I guess my point is there is no contradiction because these two sets of data are from different calculations.
Okay, you're saying that there is no contradiction, if I'm understanding you right, because one set of figures comes from like when I do my calculations at higher temperatures, and then my other set of figures comes from a set of calculations at 0 Kelvin, if I'm understanding you correctly.
Yes.
Okay, got it. I didn't understand that bit before, so I'll definitely make those changes to my results.
Excellent, thank you. Yvonne, do you want to focus attention on any other places for improvement?
No, I'm good.
Okay, anyone else wants to give suggestions to Kevin? If no, I'll quickly go over the conclusions, which were not the subject of today's meeting, but I just quickly went over it. So the sentence in the first paragraph of conclusion is not quite precise, or it doesn't have enough details. So when you're contrasting doped and undoped model, the undoped does not absorb at the band gap. But if one would excite the model at energies like twice the gap, they will be absorbing light approximately equivalently. So one may need to add specifications so that it doesn't sound deceptive. The second paragraph is quite important, and you, Kevin, may want to consult with group members, and maybe add the following thing into discussion section and keep it in the conclusions. So Kevin reports that for different data sets, the band gap law is either followed or violated. And there is no hypothetical explanation of this effect. So I would like to contribute an idea of possible hypothetical explanation. It may or may not be correct, but in case we have a band of states, the transitions from excited to ground can go subsequently from excited to the next excited to the next excited to the lowest available. And if this goes one by one subsequently, then there are expectations that such relaxation will follow the band gap law. But in addition, if the dose is if density is high, if the states do not have big offset, there is a chance that relaxation will go in parallel from the excited to the next, to the second next, to the third next. And if such parallel relaxation is enabled, then gap law will likely be violated, because the larger the number of states, the more parallel channels are made available. So if Kevin, if you have time to meditate on this thought, you may check if it will be applicable to your work. Before reading your introduction, it's not clear if reader knows what is helical model. I assume that you are meaning the nanowire grown in one direction. It will be really great if you try to identify connection between following or violating the gap law and efficiency of thermoelectrics. I do not know the answer on this question, but it will be interesting if such correlation can be found. Are there more questions to Kevin's work? If no, then I suggest that all reviewers email their comments to authors, depending on your preferred, on the way how you were fabricating the comments, either scan with a cell phone the written comments or just forwarding the file. And I suggest that for the next meeting, we all follow what Kevin did today and accomplish the discussion and conclusions sections. So the meeting is complete. Many thanks for your enthusiastic effort in both writing and editing. It is it would be impossible without this collective brainstorming session. The meeting is announced complete, and everyone is welcome to disconnect if needed. I will stay online for a couple of minutes just in case if brief one-to-one questions are needed. Okay. Goodbye, Aaron. I think he has disconnected. David, do you have anything to discuss or bring up? We do not hear you, but we can try to read the language of science.
I have a question.
Yes. I'm going to ask if I have submitted your paper or something.
Yes.
It is on my screen, and I do not lose hope to submit it like briefly. Anything else?
I mean, briefly means when?
It would be great if I can submit it today.
Yeah, because today is the last day
Yes.
of March.
Yes. Any other questions?
Okay, so I can hope soon then.
Yes.
Okay, sounds good.
Okay, thank you.
Mm-hmm. Okay, bye.
Bye. Do you have any subjects to discuss?
My question is there any work I should do for the proposal?
I'm not aware of it right now, but I will let you know. Thank you for asking. Did you watch the recordings of the meeting with Sergey?
Yes.
Was it anything valuable that we can convert into like schematic diagram, or it was not clear?
I guess it's a very simple figure. What's the point of including this figure?
I got your question. It will be not a big novelty, but since this proposal involves several researchers with a very different mindset, it would be good to have some simple things on which everyone agrees. To have some common ground that no one will dispute and agree that it is correct. So we have a dual task. One, to impress reviewers that we do something new and impressive, which is ultimately good. But on the other hand, we do not want to upset our collaborators by doing something that they do not understand or they do not support. So
okay. So this figure